This is lecture number 4. Let's begin with the summary of the previous lectures. One of the important concepts in the previous lecture was the linear operator. However, for most of you who are familiar with the basic linear algebra, you are probably more comfortable with the concept of the matrix. So what is the relation between the linear operator and the matrix? Um, in abstract linear algebra, the vector space is defined mathematically without referring to any of the physical three-dimensional or two-dimensional space. And a linear operator is also defined in that abstract situation. However, if we think about the linear operator with some basis, then that linear operator can be also represented in terms of the matrix. So that is called as the matrix representation of the linear operator. The most important part which you should not forget is that if we change the basis, then the element of the matrix representation will be different. However, the property of the linear operator will be still conserved. Also, for each of the bases, we consider the concept of the projection operator. And then if we sum up all the projection operators corresponding to all the bases, then the sum becomes equal to the identity operator, and such kind of relation was called as the completeness relation. Another useful concept related to the linear operator is that most of the linear operator can be represented as the sum of the outer product. And I also introduce some way to construct a new mapping if you are given the information such that how uh, how each of the bases will be transformed by the new linear operator. And then based on those two information, and by using the outer product, you can reconstruct the linear operator. Another important concept was the adjoint of an operator. And sometimes I mentioned that, and frequently I will say Hermitian conjugate rather than the operator. So what is the definition of the adjoint of an operator? And mathematically, yeah, the adjoint can be defined in this way, but this is not obvious. So I want to visualize the situation. So if you recall what I explained before, then we can think about some vector v in the cat space. And if we are given some linear operator, then we can also think about the result of that mapping by this operator. And sometimes we will write down this one with the more simplified form like this one. Now, let's consider the dual space of this cat vector, and then we call the vector in the dual space as the bra vector. And then obviously, the bra vector corresponding to this one is will be written with this notation. But this is not the only way we can obtain this bra vector of the result of the application of the linear operator on the vector. Another option is we can start with the bra vector corresponding to this cat vector in the dual space. Then there might exist a new operator which will map this bra vector to a new output vector, output bra vector, and then this one will make sure that the result of this linear transformation will be the same as this vector. So if we can find such kind of vector, such kind of operator, omega, some kind of vector operator, then we will um, um, write this operator using the dagger notation. So if the original operator was written as omega, then we will write that corresponding new operator as omega dagger. And of course, this omega doesn't necessarily to be the same as the omega dagger. However, and then also, yeah, this is conceptually correct, but it is not easy to imagine what really happens to the this operator, uh, or what is the relation between this adjoint and the original operator. And if we find out the element, matrix element of this adjoint or Hermitian conjugate of the original operator, then the situation becomes much simpler. What I mean by that is that if we are trying to find out the each element, then we have to calculate the inner product of two basis vector with this operator between them. Then the new element of the new matrix representation of the this adjoint will be actually the transpose and the complex conjugation of the matrix representation of the original operator. Now, yeah, I said that this new operator doesn't necessarily to be the same as this original operator. However, if they are the same, then we call such kind of operator as Hermitian. And this concept is very similar to the symmetric matrix when the each of the component is a real value. Another types of the another types of the operator we can think about is that sometimes the Hermitian conjugate of the original operator is the inverse operator of the original operator. So if we multiply them together, then they will lead to the identity operator. And then we call such kind of operator as a unitary operator. And the concept of unitary operator is very similar to orthogonal matrix in the when the matrix has only the real values. We also discussed the trace of the matrix, and then we also proved that some of the important properties of the trace. And finally, we started a discussion about the eigenvalue problem. And eigenvalue problem is written in this way. So we start with, if we are given some arbitrary linear operator, then we might be able to find some vector um, such that if this operator works on is applied on this vector, then the output vector will be still parallel to this vector, but the length of the vector output vector is not necessarily to be the same as the original vector. So we will always have, we might always have some scaling factor in front of that original vector, and if we can find such kind of combination of the this vector and this value, then we call this vector as the eigenvector of this operator, and we call this scaling factor as the eigenvalue corresponding to that eigenvector. And if we think about this problem involves a lot of unknown values because it is not the only the this eigenvalue, but each component of this eigenvector are unknown. So instead of trying to find the instead of trying to solve this complex problem as it is, we can, if we turn this if we write down this equation in terms of the matrix elements or using the matrix representation, then that problem, the eigenvalue problem, will turn into this kind of matrix equation problem. And to satisfy that, to make that every component to be zero on the right-hand side, then the only option, the only trivial solution, if we want to have any trivial solution satisfying this kind of multiplication problem, then the only way is that we should not have any inverse matrix correspond of this matrix, and that such kind of requirement turn into the determinant problem. So by requiring that the determinant of this matrix becomes 0, then we should be able to find out the omega, which is the only unknown variable in this problem. And once we found out that eigenvalue problem, then we can plug in back here. Then we can find out these unknown vectors as well. So that's what we learned in the previous lecture. So today we will continue from the eigenvalue problem, and then we will discuss more important properties of the with the eigenvalue problems. In the last lecture, at the end of last lecture, we actually solved this problem, and then from the solution, we obtained the result something like this one. So there are three. We found out that there are three distinct eigenvalues, which is 1 and plus minus I, and the corresponding eigenvectors were obtained in this way. And at that time, I think I did not point out, but yeah, one thing you should notice here is that all these eigenvectors are orthonormal to each other, and also they are linearly independent of each other. So those are very important fact which we will use in today's lecture. But in this case, because all these three eigenvalues are distinct from each other, so we in this case we say that all the eigenvalues are non-degenerate. However, today we will also see the degenerate case, and then see what's the difference compared to the previous result. So today, new problem. The another linear operator looks like this, and then let's also try to find out the eigenvectors and eigenvalues. To solve the eigenvalue problems, the first thing we have to do is find out the solution for this determinant relation, which is minus omega minus omega sub I, which can be represented as 1 minus omega 0, 1, and 0, 2 minus omega 0, and 1, 0, 1 minus omega. And this is the another rotation for the determinant. And in this case, the first thing we have to do is find out the for the multiply this factor, and then find out the 2 by 2 determinant, which is now 2 minus omega times 1 minus omega minus and 0, 0. So we can just ignore that part. And typically, the next thing we have to do is use this one, and then using the other these 4 factors to find out. But because this is already 0, so we will just skip. And then finally, for this component, generally we have to multiply 1, and then also again we have to find out this submatrix, and then find out the determinant, which is AD, which is 0 minus the product of these two. And then for that case, we can just replace this part. Well, let me also, one is nothing. So it is 2 minus omega, something like this one. Now we have the common factors of 2 minus omega part. Then we can expand this square, which is 1 minus 2 omega plus omega squared. And from this one, we obtain also this factor. So 1 and minus 1 will cancel with each other. So finally, and then for this one, this can be collected as omega times omega minus 2. And we also note that this is also another omega minus 2 with minus sign in front of it. So from this one, we obtain the relation that we obtain the fact that for this determinant to be 0, then either omega equals 0 or omega equals 2 is the solution. So let's find out the eigenvector corresponding to omega equals 0. So in this case, we have to rewrite this omega minus omega I matrix. So that will be 1 0 1 0 2 0 1 0 1 because omega equals 0, and then we have to find out x1 x2 x3, and which will become 0 0 0. So in this case, if we expand, if we find out the multiplication, then it is x1 minus x1 plus x3 for the second one, 2x2, and the last one x1 plus x3 again. So yeah, from this from the second relation, second equation, we can immediately obtain x2 should be 0. And from the first equation, the third equations are the same. So, and then from this one, we can obtain the x3 should be minus x1. So based on this result, we can conclude that x1, x2, x3 can be simplified by using this one. So x1 does not have restriction, and then x2 should be 0, and x3 should be minus x1, which means, oh, sorry. So x1 and 1, 0, minus 1. So this is the first eigenvector corresponding to omega equals 0. So in this case, we found out the eigenvector having the eigenvalue of 0. So we can either write down in this way, or we generally prefer to have a normalized vector. So yeah, we should divide by this vector. So that is the first eigenvector of this operator. And what about the omega equals 2? Note that this omega equals 2 is actually, it has a multiplicity of 2 because we from this determinant equation, we know that omega 2 is actually it is a duplicate. So yeah, this one has two factors. Then let's see what happens with the with this guy. So yeah, we will have the different values for each of these. So let's remove all these. Then what happens? So with the omega equals 2, then 1 minus omega is minus 1, and this one becomes 0, and this one is again minus 1. So if we expand again, then it is minus x1 plus x3, and for this case, it is just a 0, and then it is x1 minus x3. And again, from this second equation, we do not get any further information. And from the first and third equations, they are the same. So they have the same information, which is x3 should be the same as x1. So based on that one, what we can conclude is that x1 has no restriction, and then x2 also does not have any restriction compared to the previous case. So we have this option. And what about the x3? It should be the same as x1. So yeah, if I write down in this way, then I can also split this one into two linear combination of two vectors, like this one. So here, what we have to notice is that any linear combination of these two vectors will still satisfy this original eigenvector problem. So and then that means that the solution of the eigenvector problem with this eigenvalue forms a space, a vector space, and then that vector space is spanned by these two bases, these two basis vectors, and these two basis vectors are linearly independent. You can immediately see that they are linearly independent, and also they are orthogonal to each other. And you would also notice that this is actually by sometimes it is by accident that they turn out to be linearly orthogonal to each other, but generally you get that any of the linearly independent result. And also you should note that these vectors are always orthogonal to this one. Yeah, and then the reason we get such kind of orthogonality is not by the accident, but it is actually required if our given matrix are the form of the is the Hermitian operator. So yeah, we will formally prove such kind of relation, but you can immediately see that such kind of relation is automatically satisfied between these three vectors. And another thing is that previously for the omega equals 0, we only used a single label. However, for this case, omega equals 2, there exist two linearly independent solutions. So in this case, to distinguish these two solutions, we need additional index. So instead of writing down just omega equals 2 cat vector, we would use one more index, which means 1 and 2. And then the first one, yeah, of course, I can choose whichever I want. And let me just choose this one. And then let's normalize this one. And another eigenvector, which is this one, then this one will correspond to 0, 1, 0. Yeah, something like this one. So now we obtain three eigenvectors, and then again, yeah, these two eigenvectors are degenerate, meaning that they have the same eigenvalues, but except that, yeah, they are orthogonal to each other, or yeah, we can always find out the combination of the orthogonal um, vectors if we have multiplicity of the eigenvalues. And then such kind of multiplicity is called as a degeneracy in quantum mechanics. So this page summarizes what we just learned. And let's use the concept of the degeneracy or non-degeneracy in the next pages. So the first property we want to show is about the Hermitian operators. And then the first claim I want to make is that all the eigenvalues of the Hermitian operators should be real. And how can we prove that? Well, yeah, let's assume that omega is the Hermitian operator, and assume that we already found some eigenvectors of this Hermitian operator, and then we will call it as a omega vector, and then the corresponding eigenvalue will be also written with the will be noted with the omega. Then what we can do is apply the same eigenvector from the left, and then yeah, this is just a very simple relation. Then next thing is we are going to take the complex conjugation of both sides. Then how can we obtain this relation? Well, let's see some general property. So so assume that we are calculating some inner product between the two vectors and some linear operator. Let's say that they are v omega v and v bra, and then linear operator omega, and then another vector w. And then here we are not assuming any kind of special property. So my question is, what happens if I take the complex conjugation of the entire value? Well, the first relation we should remember is that this one is sometimes written with this kind of notation. And then next relation we are going to use is the skew symmetry. So with the complex conjugation, we know that this can be rewritten in this form. And finally, this one, yeah, can be also written with this form. And then this result comes from the definition of the Hermitian conjugate or adjoint of a given operator. So this is a very general relation between the for the linear operator and then complex conjugation. So and then yeah, this kind of relation should be valid even when the both of the vectors are the same. So yeah, if we apply this one, this relation to here, then this is very natural. And because it is equation, we should also take the complex conjugation of this side as well. Yeah, so what we are doing is here, and then from this one, omega should be become the complex conjugation of itself. And what about this guy? Well, they are the same. So with the complex conjugation of, applied to the inner product, we should exchange their location, but that means that they will be the same. So that's how we obtain this equation. Then what about this one? How can we obtain this one? Well, yeah, here I'm saying that yeah, this one we ignore this dagger to here. And how can we do that? That's because I assume that omega is the Hermitian operator. So the definition of the Hermitian operator is that complex Hermitian conjugate of the operator should be the same as its original operator. So this is where I can, that's why I can go from here to here. Then finally, how can I get this one? That's because I started with this relation. So if I replace this omega with this one, then we will obtain this one at the final stage. Then then from this one, how can we prove that omega, eigenvalue omega should be always real? Well, that's quite simple, straightforward. Because from this one, we can rewrite the relation such that uh, omega should be 0, and then for this product should become to become 0, at least one of them should be 0. And then we know that this omega is this omega vector is the eigenvector, which is non-zero vector. So this inner product of itself cannot become 0. So the only option we have is that this vector should become 0, which means that omega and its complex conjugation should be the same. And we call such kind of value as a real. So that's how we can prove that all the eigenvalues of the Hermitian operator should be real. Another interesting property based on this fact is that if there is no degeneracy, meaning that all the eigenvalues are different, or at least between whenever eigenvalues are different, then we can claim that the eigenvectors corresponding to those different eigenvalues are always orthogonal to each other. How can we prove that? Well, that's also very simple. So assume that imagine two eigenvectors with different eigenvalues. So I'm saying that there is omega I and omega j, which are different values, and then there should be always a corresponding eigenvectors. So we will always have this kind of relation. And then what we can do is multiply omega j on the right hand side of this equation, like this one, and also simultaneously we apply this vector on the right hand side of this one. Then we will obtain this second equation. Now, what we can do is take the complex conjugation of this guy, entire part. Then we know that this one won't change. The result of this one will be the same as this one, because we already saw that the complex conjugation of the inner product means that everything will change their location, and then the linear operator will become a dagger or a joint of the original operator. But we are assuming that all the operator we are considering is Hermitian operator. So that dagger will be cancelled. So the complex conjugation of this guy is the same as this one. Then what about the right-hand side, two components? So this component should be the same as this one. And this one, yeah, if we take, if we apply the complex conjugation on each of the vector, then this one should become omega sub I star. But I didn't use the star. Why? Because I said that any eigenvalues of the Hermitian operator should be real. So it doesn't matter whether I have a star or not. So I will have this one. And for this one, because this complex conjugation will apply to this one, and then now they will switch their location. And the final result is this one. And I just wrote down this one again. So they should be the same. So from this one, yeah, I can collect the common factors like this one. And then the conclusion is that the product of these two factors should be 0. And now we already assume that we are considering that all the eigenvalues are different from each other, which means this factor cannot be 0. So who should be 0? This one. So from this relation, we can conclude that all the eigenvalues with different all the eigenvectors of the Hermitian operator should be orthogonal to each other when they have different eigenvalues. So yeah, the proof is based on the fact that the eigenvalues are real. Another important property is that based on these properties, we can also prove that for every Hermitian operator, there should be there exists a basis consisting of its orthonormal eigenvectors, and in that eigenvector, in that basis, the matrix representation of the Hermitian operator will always appear as the diagonal matrix, and then the diagonal term will be filled with the corresponding eigenvalues. So, well, the full proof requires requires us to consider even for the degenerate case, but then the proof becomes too long. So for simple proof, yeah, so this is the partial proof, but for the simple proof, I will simply assume that there is no degeneracy, and then you can get some intuition, then you can refer to the reference of page 36 of the reference for the full proof. So let's see the proof for the simple case. Non-degenerate case. If we recall that the matrix representation of omega should be will be written in this way, and from this fact, we are assuming that all the bases 1, 2, 3, 4, yeah, they are all the eigenvectors of the of this operator. Then it should be obvious that this one, yeah, because it here the this operator is working on being applied to the first eigenvector, which will turn into omega sub 1, 1. And this one, omega 1 is just an eigenvalue, and then 1 and 1 are normalized. So eventually, they will just become 1, and then the remaining value will be omega sub 1, something like this one. Then what about this one? Well, 2 is another eigenvalue, eigenvector of the omega. So the result of this one should be omega 2, 2. However, now omega 1, eigenvector 1 and eigenvector 2 should be orthogonal to each other. So and then here I was assuming that the this is the non-degenerate case. So there should be no non-orthogonal eigenvectors. So the inner product between 1 and 2 should be 0. So everything will become 0 here. And the same logic will apply to everything here and here. So everything will become 0. Everything here 0, 0, 0. What about here? What about this guy? In this case, this will apply to here, which means omega 2, 2. Now, this omega and this omegas are orthonormal um, vectors, and then they are the same. So their inner product will be simply 1, and then we will be just left with omega 2, which means that this diagonal part will become omega 2, and the same argument will be applied to everywhere here. So that's the simple proof. But here again, I assume the case for the non-degenerate case, and then for the full proof for the including the degenerate case, then you should refer to the reference. Another important type of the linear operator is the unitary operator. And there are two important properties of the unitary operator. The first thing is that the eigenvalues of the unitary operator are generally a complex number, and the absolute value of that complex number should be 1. Another important property is that when there is no degeneracy, similar to the Hermitian operator, the eigenvectors of the unitary operator should be mutually orthogonal. The proof of these two theorems can be actually proven by similar step. So I will start with the common proof first, common steps of proof. So similar to the proof of the Hermitian operator, let's start with the two eigenvectors of the the given unitary operator, and then this u sub I is the corresponding eigenvalues of the this vector, and then u sub j is the eigenvalue of this eigenvector. Now, what we are going to do is that find out the complex Hermitian conjugate of this part. So let's try to find out this part, and this one can be found easily because that one can be also represented using this notation, and then based on the definition of the dagger notation, that means that this one will be rewritten in this way. Then what about this right-hand side? Well, that's also simple, because if you remember that to find out the bra vector, when you are given the linear combination of the cat vector, the only thing you should be careful is that make sure to convert the coefficient to the to its own complex conjugate. So this part will become, this right-hand side will become uj star u sub j. So that's all you have to remember. Then now what we can do is that we can consider taking the inner product between this vector and this vector. Then to find out the bra part, this is given in this way. So this half of the part comes from the corresponding bra vector of this part, and then this another part, another half came from here. So on the right-hand side of the equality, we should also use this property coming from here, and then this one to here. Now, up to this moment, I didn't use the property of the unitarity of the given operator U, but the definition of the unitary operator says that this product should become identity. So that means that we can ignore this part, which means I sub j times I sub u sub I. U sub j inner product of the u sub j and u sub I, which is here. So from that simple relation, we obtain this relation. Then by moving this part to the left-hand side, we can have this relation. Now, how can we prove the theorem 11 and 12? Well, that's very simple. To prove theorem 11, all we have to do is assume that this I and j are the same, which means that if this is the same, then this inner product of two vectors means that the inner product of the same vector. And we know that this is eigenvector. So this corresponds to the, this is proportional to the magnitude of the vector. And because the vector is non-zero vector, this part cannot be zero. So the only way to make the entire product to become zero is to make this part to zero. And if I and j are the same, then this one will turn into this one. And do you remember the what this? Can you see the meaning of this one? All it says is that this one corresponds to the square of the absolute value of this u sub I. So the magnitude of the magnitude or absolute value of this eigenvalue should be also zero, also one, which implies that it should be a complex number of unit modulus. Then how to prove the theorem 12? Well, now, if we assume that I and j are not the same, in that case, this value cannot be 1 because this can be 1 only when I and j these two indices are the same. So to make this entire equation to hold, the only option is to make this product, this inner product should be 0, which means this one. And what's the meaning of this one? Well, the inner product of two vectors is 0 means that two vectors should be orthogonal to each other. So yeah, the theorem 12 is naturally derived. Then, well, yeah, when I learn this property and the orthogonality of the eigenvectors of the Hermitian operator, I was a little bit confused because unitary operator and the Hermitian operator are different. Then how can we have such a common property that the eigenvectors are always orthogonal for both of the case? Well, the answer is these two types of operator belong to another type of operator, which is called as a normal operator. And the definition of the normal operator is like this one. And you can verify that unitary and the Hermitian operator belong to satisfy this relation. And then you can generally prove that any the eigenvectors of the any normal operator will be always orthogonal to each other. And then the proof is a little bit long, so instead of proving it by myself, yeah, you can refer to the textbook, main textbook. This is not the principles of the quantum mechanics, but the main textbook by Isaac Chuang and Michael Nielsen. Then, what is the application of the unitary matrix? Probably one of the most popular application of the unitary matrix is it is used for the basis transformation. So let's consider the basis transformation. So let's start with some concrete example. Assume that we have some basis, also normal basis 1 and 2, and inside this basis we have some vector v, and then this vector v can be represented as the uh, with the vector component v sub 1 in 1 and v sub 2 for basis vector 2. However, this is not the only orthonormal basis we can think of. There will be a lot of options. For example, this one is a new orthonormal basis. Assume that this is Roman number 1, Roman numeric 1, Roman numeral 2. Then the same vector v can be also represented in terms of this new basis, v sub Roman numeral 1, v sub Roman numeral 2. And then the next question is, well, we know that this v sub 1 in Arabic numbered base or the new original base, and then this new component, they should have a well-defined relation. So what is the relation? Well, the simplest example is we can just try to find out this v sub 1. This, and then this can be immediately found by taking the inner product between a 1 and original vector v. Then this one we can also apply to this second representation. So it will be 1 plus v sub 2 and 2 2. Similarly, v sub 2 is 2v, and v sub 2 2 1 plus v sub 2 2. Oops, there was a mistake. Yeah, it was 1, and now it is 2 and 2. So and this kind of relation can be also rewritten in terms of the matrix form. So v1, v2, and then there will be some matrix, and then the new component vector like this one. So then this each of the component will be something like this is 1 1, and this is 1 2, and this is 2 1 2 2. So this is they can be always represented in this way. Then the next question is, this is matrix, but we also know that matrix will always have operator form. So then how can we find out? And then I always mention that the matrix is kind of representation in some given basis. So can we find out the original operator corresponding to this some given matrix? And the answer is yes. And then how can we do that? Well, the first thing we should consider is that if I consider this one as a matrix, and then for whenever I'm writing down whenever I'm talking about the matrix explicitly, then I would use this kind of notation. Yeah, so instead of writing just like this, I will just have the double line. Then the first the 1 2 component of this one is this one, which means 1 and Roman numeral 2. And then generally, if I'm looking for some ij's component, i's row and then j's column component, then they should be something like I and j in Roman numeral form. And then for notational purpose, I will use the capital alphabet to represent the Roman numeral, and then the lowercase alphabet to represent the Arabic number. Then what this means is that generally, if we had some operator, yeah, if we had some operator u, then the ij's component will be generally found by taking this kind of inner product. So from this one, then how can we, yeah, so how can we always guarantee that this uj multiplication will turn into the Roman numeral basis or a new basis? Well, this is actually quite simple. If we define u in the form of the Roman numeral outer product with the Arabic or original basis, and then new basis in vector in the new basis, and then um, the vector in the original basis, and then so forth. If we add all of these outer products together, then if I just apply the cat vector on here, then yeah, only the j's component, j's part will survive, and everything else will be just disappear because they are orthogonal to each other. So we will always obtain. So we will, yeah, with this one, with this definition, then we would always have u j will turn into the Roman numeral basis, something like this. So yeah, in other words, the operator corresponding to this basis transform matrix has the form of summation of all the new basis vector with the in terms of the outer product with the original basis vector, like this one. So this is one result. And then the next thing I'm going to claim is that this operator u is actually always a unitary operator. How can we prove that? Well, the proof is quite straightforward, as we can see here, because to prove that something is unitary, the only thing we have to prove is that the inner product, not the inner product, the multiplication of the matrix with its own adjoint will turn into the identity operator. And then, as you can see here, well, yeah, let's see, try to use that a simple example. Yeah, then it is something like this one. And then the adjoint of this one is that they will just switch the location. So something like this one. Then if we use the distributive property, then this one will survive because they will just turn into one. So it will become like this one. However, for the inner product between this one and this one, they will cancel because they are orthogonal to each other. So they won't survive. And similarly, for the second term, this one, the inner product of this one will become 0, while this one will turn into 1. So only the second term will survive, like this one, and so forth if we had more terms. And what does this summation look like? It is simply an identity operator. So yeah, with these simple lines, we can prove that this shape will always be a unitary operator. So we can generalize that the component in the original basis and the relation between the or the transformation between the vector component in the new basis and then the original basis can have this form, which means that the width of I can be always represented as the um, um, as the I j and width of j. Yeah, so here the capital, yeah, again the uppercase alphabet represent the Roman numerals, and then the summation goes over the j, and then this one can be also um, um, repre we yeah, we can also write this one as something like this one. Ij's component of the um, Ij, Ij's component of the matrix representation of this unitary operator. And so yeah, this is the transformation of the vector component. Then what about the transformation of the matrix representation element transformation of the element of the matrix representation of some operator? So now, yeah, let's think about some operator omega and think about its matrix representation in the in this origin in this original basis. So to obtain such kind of value, then what we have to do is take the inner product of between these two bases, which we frequently also use this notation. And the next question is how this component or how is this matrix representation in the original basis will be transformed into the new basis. And to find out the relation, yeah, we can just calculate the inner product not between this old basis but in between the new basis Roman numeral basis ij, and then we want to connect this value to the original value. And to find out this one, the relation, the proof is simple, or the procedure is simple. All we have to do is add identity operator between here and here. So that means that now, yeah, this is identity operator, while this is the um, index of the Roman numerals. So yeah, what we will get is that summation. Yeah, so the this yeah, using the completeness relation, this identity operator can be, yeah, written as the summation of these all the projection operator, and then omega, and another summation of the projection operator, and finally this one. Then there are double summations, so I can just pull out the summation notation outside here, and what I have is I small k and k omega L, and then L J, something like this one. And then the I know that this component Lj is the component of the this one. So what we can also represent this one as is use of Lj. And what about this one? It is the complex conjugation of the yeah, this is the complex conjugation of this one. And then now, yeah, this one, we know that this is the unitary operator. So the relation is that this part, yeah, so that one is summation over K and L index, and this is the U dagger of the I case component, and this one is the K L's component, and finally this one is a U L J component. Yeah, you can also probably use this notation. So eventually, this the overall relation can be also rewritten in this form, and then the multiplication of three operator, and then the component is ij's component. So what we obtained here is in the new basis, if we are trying to find out i's and j's component of the of the operator in the new basis, then that value can be obtained by calculating this kind of matrix. Well, this is probably better. Yeah, so you should find out the matrix multiplication in the original basis. And then yeah, so yeah, for this one, yeah, let's summarize a little bit more systematically. So in a typical situation, most of the operators will be given in a matrix form. So if we want to think about the matrix form of this one, this operator omega, then we can use the notation something like this one, and then this is the matrix representation of omega in the original basis, and then assume that we represent the new representation of the same omega in a Roman new basis, or Roman numeral basis, something like this one. And then this part is this, and this one is correspond. This one is this one. So and then here, yeah, U is the matrix representation of U in the original basis. Yeah, so each of these components are the matrix representation of U. And then the next question is, um, what is this guy look like in the 1 and 2 basis? So yeah, the only way to find out is we just calculate ij's component, and then that means that I u j, and again, yeah, we can just add use the completeness relation. No, sorry, not the completeness relation, but we have the definition of u, which is here. So if I replace that one with that summation, k, small k, and then the j, then this will be well, and then we know that this is the same basis, same old basis, original basis. So this will become non-zero only when k and j are the same. So this is the Kronecker delta. So yeah, the summation is not necessary, and then we know that this will eventually turn into um, um, I I basis in the original basis and basis vector, and then J's basis vector in the new basis. So if I write down this one in the matrix form, then we know that this will become something like 1, 1, and 1 in Arabic number, 2 in Roman numeric, and so forth. And the second line will look like this, and third line look like this, and so forth. And then if we think about what this column represent, it is the vector representation of the new basis vector I in the old basis 1, 2, 3 in Arabic numbered basis. So we can say that this basis transformation matrix has its column, and well, yeah, I can say that the basis transformation is composed of the columns, and each of the column is the vector component of the new basis vector in terms of the old basis. Yeah, so yeah, I think it is a little bit confusing, but if you think about the situation carefully, then yeah, you'd understand the situation. Okay, so yeah, let me finish. Let me stop for today, and then I will continue in the next lecture.